A final key component in any titration method is standardization, and so we need to talk about primary standards. We use standardization in many techniques, titration just being one of them, but in relation to titration, standardization means that the titrant must be of a known concentration, right? Our accuracy for this method is going to be determined by the fact that we have to have a known concentration of NaOH in order to determine the concentration, the unknown concentration of the acid. So we need to use a primary standard to determine the concentration of the titrant. Characteristics of primary standards include they must have high purity so that when you mass it out, it's actually truly representative of the moles of substance that are present. So you don't have, 80% purity and 20% of the mass that you're weighing out is due to contaminants of some kind. It needs to be stable and non-reactive. So if it sits in a jar in the stock room for 4 years or 5 years or 20 years, we know that it's not going to be reacting with the air around it and creating new compounds. We need it to be stable over time. It should have a high molecular mass, and that's going to minimize massing errors, so on the balance. And then it should be non-hygroscopic. And so hygroscopic means that it takes up water or adsorbs water. So we don't want a substance that will adsorb water to the surface. Otherwise, the mass that you're weighing is not due only to the standard, but it's rather due to standard plus some water that's present. So NaOH is actually a really bad primary standard. We don't use sodium hydroxide as a primary standard because of these issues. So, for example, I have 3 balances here. They each have 5 grams of sodium hydroxide on them. And sodium hydroxide is actually fairly hygroscopic. And so if it sits long enough, water molecules will adsorb to that solid sodium hydroxide, and it will change the mass of the sodium hydroxide that's present. So sodium hydroxide is hygroscopic. It's also fairly reactive, and carbon dioxide in the air will react with that sodium hydroxide and make sodium carbonate. So carbon dioxide will adsorb to the surface, it will react with sodium hydroxide, and it will change the mass of the compound that's present. So sodium hydroxide is not a good primary standard because it is both hygroscopic and highly reactive. And so instead, we use potassium hydrogen phthalate. It's abbreviated KHP, potassium hydrogen, and then this is not meant for phosphorus. This is meant to indicate phthalate. Here's the molecule, okay, potassium, and here's the hydrogen and the phthalate part. It has a super high purity, 99.95% pure. It has a high molar mass of 204.22 grams per mole. It is stable over time. It's not very reactive at all, and it has a very low hygroscopicity. In addition, if you're really concerned about this adsorbing water, then you can also put it in the oven for a little bit and evaporate all the water off. We don't usually have that problem. And so how we do a standardization is we make our NaOH solution. We follow the titration method the way it has been described to you before. We are going to have a known mass of KHP, which means we have known moles of KHP. So here's some little KHP crystals. And I can use the mass that I find from the balance and divide it by the molar mass to get moles of KHP. And I just dissolve that into water in my flask. That's going to be my analyte. Okay, I'm going to do my titration. I'm going to add my sodium hydroxide to a certain volume until I get to the end point or the equivalence point. So maybe it took me 37 milliliters to get to my end point. Therefore, I have a known volume of NaOH, but I have an unknown concentration. I have an approximate concentration just based on the mass of sodium hydroxide that I weighed to make my solution. But I don't really know precisely what it is. So that's what we're solving for here, the unknown concentration of sodium hydroxide. So I use all of the calculation skills that we learned in the previous 2 videos. which is to say I find my moles of KHP, I use my balanced chemical equation to do a conversion factor between KHP and NaOH. Now that I have my moles of NaOH, I can divide by the volume of NaOH that I used to get to that equivalence point, and that gives me my concentration of sodium hydroxide. In lab, you'll be doing one standardization run so that we can focus on getting statistics for using the burette and an indicator versus the digital version, which is the drop counter, the vernier drop counter.